My name is Joe Rakuya. I'm the inventor of the perfect concrete wall system, which is used to enclose buildings. Today's recording is May 2nd, 2021. And I'd like to start the presentation with a brief introduction of myself. I'm a registered structural engineer in the state of Ohio. I'm also an accredited professional with LEED, Building Construction and Design, and I have 45 years of construction management, design, inspection, and forensics experience in Central Ohio. The point of today's presentation is to give you an idea of what my invention is. It incorporates the longevity of concrete in the wall system. It is of extremely high quality due to the nature that it is totally visible all at one point. There is much less field labor involved. It's a very energy efficient wall. It delivers very high indoor air quality due to its components. The framework is manufactured off-site with modular components, which allow it to take advantage of manufacturing technology in quality improvement. And the framework is internal and negates the need for expensive forming systems. Therefore, it is less costly. This is a slide of my contents of today's presentation. We went over the introduction. We're going to talk about market position, description of my perfect concrete building enclosure apparatus, the benefits, and closing. The market position I envision are for universities, healthcare, hotels, and residential. And why is that? Well, these buildings require the following performance criteria: high indoor air quality, comfort to occupants, energy efficient, and longevity. The prioritized attributes of an effective building envelope. The highest priority is the water control layer. The second is the air control layer. Third, vapor control. And lasting, thermal control layer. In other words, if your exterior building enclosure lets water in, it doesn't matter how good any of these other things are, it's going to be a complete failure. So in taking these priorities, I've compared rationally the different building enclosure systems on the market. So down along this column are the attributes, and the top row are the different current building enclosure types: cavity wall masonry, IFAS, metal panels, thin veneer, precast, cast in place sandwich wall, and the perfect concrete building enclosure. Now, I rated these different systems. Like a cavity wall masonry is the barrier for water control interrupted, and it is when you build a masonry wall. So I gave that a negative, or red. And if it is neutral, I give it a yellow and a number score of 0. And if it's good in that area, like a masonry cavity wall does dry to the inside, I give it a green or a 1. So I rate all these systems and I sum up the numbers, and the two high ones are precast and cast in place sandwich wall construction, and my system, the perfect concrete building enclosure, just knocks it out of a park with a 17. So basically, the perfect concrete building enclosure has the best of precast systems and cast in place sandwich wall systems. It meets all their desired attributes, and those attributes, which would be high indoor air quality, comfort to occupants, energy efficient, and longevity. The best features of cast in place sandwich walls. The thermal barrier is encased in concrete and protects the structural life of the wall. The vapor barrier is encased in concrete. No fitment issues in the field since it's cast in place. No hoisting of heavy precast panels. And it's a cleaner design details at various transitions throughout the wall. So how about precast panels? Well, it also has the best attributes of precast: reduction in field labor, reduction in project duration, quality control is greatly simplified, precise reinforcement, can also use composite reinforcement, continuous insulation, sustainable shuttering, and no expensive form system to truck and maintain. So I just want to talk about a little bit more about concrete building enclosures. Back in 2018, Hurricane Michael hit the Florida Panhandle coast, and this is the area it came into, right dead on this building here. As you can see, it just wiped out everything around it. This building was a cast-in-place building, cast-in-place concrete. And building enclosure is a modular system. The framework is made up of several standard components that are made in a factory and assembled in a factory per a set of shop drawings that are approved by the contractor and the architect. Modular fabrication is ultimately a manufacturing process that the construction crews can finally tap into to increase productivity and quality and reduce the amount of field skilled labor that is required. So quality, price, and time are all improved by using modular. So here is a sketch taken right out of my patent file showing the system. And the next slide is I'm going to demonstrate it with an animation. So here we are, starting with a footer. It's time to show you the apparatus in use. I first would like to start with the end in mind, a sample project of 2 straight walls at a particular length each and an outside corner, just for simplicity. And these walls are going to be setting on the form footer that you see that has vertical rebar dowels sticking up. Now this very well could be the 3rd or 4th floor of a building that we start with, but for simplicity's sake, we're going to have 2 straight walls, particular length and height, and an outside corner. Now, the shop drawings have all been approved. The panels have been manufactured and shipped to the job site. Now it's time to start building this little project. So first thing the crews will do is set the 2 panels, the straight wall panels, that are a project-specific height and length. and they set them in an exact location on the footer, and they get bolted down through these little feet to the footer. The next step is to insert the corner module. In this case, it's an outside corner, and there's two friction fit H members that get attached to the rigid insulation panels, or rigid insulation partitions of the panels. And that's how we get a seal from one panel to the other. Okay, the next step for the field is to insert the horizontal bars as called out on the engineer of records drawings, both in the exterior partition and interior partition. You can see that better here. And remember, we have these rebar locators that locate the bars, the exact location from the outside face of the concrete. Now, the next step for the field crews is to install the shuttering. Well, one more step before that. Let's go back a minute, and I want to make, because this is one of the important things. Now, all the bars are installed, the horizontal, the vertical. If there is any electrical or mechanical embedded items, everything is done, ready to go. At this point, an inspector or a quality control officer from the contractor's crew can visually inspect every component, the seals, the fitment, the rebar spacing, everything, where the electrical goes inside and outside for this wall prior to concrete pouring. This is one of the beauties of this system. Quality control is made very, very simple. So now we can install, once the quality control officer, the contractor or inspector has visually inspected everything, the shuttering can be installed. In this case, it's plywood, 3/4 inch plywood. And it gets fastened to these struts in these vertical flanges. These flanges are 3 inches wide, and as you can see, there's standoffs to keep the shuttering 3/4 of an inch around off this face. That way, concrete completely encapsulates the trusses. So the next step in the process is to pour the concrete. Concrete is poured, and this is a cutaway, of course, but you can see there's two separate individual partitions of concrete. In this case, the project documents called for a 4-inch width of concrete on the exterior and an 8-inch on the interior. These are connected through these shear connectors. These shear connectors go all the way through, and you can see how it works right here. But they're completely embedded, and they're tapered to withstand the tensile loads and to make these two partitions act together as one concrete wall with less concrete. Shuttering is removed, and you can see you have a nice clean concrete face on both the interior and exterior. And the other nice thing about this is that you can visually inspect how well the consolidation job the crews have done. So there's never any worry that it stays completely covered. And also on the exterior. So that is it. And now we'll do a demonstration of the model being fabricated. This 3D model that I showed you was after all the manufacturing was done and the panels were shipped to the job site, how they are used. Now I'm going to show you how the panels get assembled in the factory. Now to make a straight panel, there's three components. There's the rigid insulation partition. There is the vertical truss member, which is the heart of the system. And to connect the panels together out in the field, there is a plastic H-shaped connector device, this yellow thing right here. So let's see how one of these panels get assembled. First, it starts per project cutting the piece to the correct height, and the spacing for this particular panel is 12 inches. So this panel is 12 inches in this direction, and the height is called out on the shop drawings, the approved shop drawings, which I'm going to show you an example of later on in the presentation. The next step is to take this rigid insulation partition and cut grooves into it. These grooves are precisely cut, and through manufacturing, a system can be developed, either a hot wire or a laser or some other method, whatever would be most economical and quick to do. Now, it's also done on both sides, as you can see. So the next step is to cut the pre-made trusses, vertical trusses, to height, so that this height matches the approved shop drawing. And as you will see, these trusses have shear connectors that go all the way through there, through the rigid insulation, and provide two things: support of these flanges during the short duration liquid state of concrete, and the long-term shear connection capability to allow the two concrete partitions to act together in composite action. Also, these trusses have feet on the bottom, which have holes for attaching to floors, or in the case we showed previously, was a footer. As you can see, it is symmetrical around the center line, so it can be easily manufactured with an injection molding system. The next step is to spray the rigid foam pieces that we grooved with an adhesive and attach it to the vertical truss. And as you can see, it's a real tight fit. The next step is to bring in another rigid insulation partition and spray adhesive the same way. And this process is completed until the length of this panel matches the length on the shop drawing. Once it is done, the factory will mark on the top what mark number, so it matches the shop drawing. Now, connectors, these are slip-on connectors, will be attached in the field. They are friction fit, and they are quite easily attached by just sliding them right on the rigid insulation, as you can see, just like that. And then the next panel is slid right into it. So that's how that works. And that is the system during manufacturing. The beauty of this is that the separate components, the 5 separate components, can be manufactured ahead of time and cut to the appropriate length for the assembly process, and take advantage of manufacturing technology to continuously improve the quality, the fit, the cost, and the duration, and also look at other materials in the future. Okay, the The next step is to show you the shop drawing phase. Obviously, the last two 3D CAD models were representations of how the field assembles the panels and how the manufacturing plant would assemble the various components to make the panels. Well, what happens before that? Well, there's a typical shop drawing process. And what you see here is an architectural drawing that gets submitted to the client, and there's also a foundation plan, which looks like this. The foundation plan has all the lengths, dimensions, top of wall marks, any penetrations that are listed. We're going to look at this wall right here and show you what a shop drawing layout plan with all the different pieces would look like. So here's that wall right here. It's made up of one outside corner and one inside corner, both 2 foot by 2 foot, which is our standard module for corners. And the wall panel is exactly 24 foot, 34 inches long. And the top of wall is 8 foot and 1/8 of an inch high. So this would be submitted to the contractors and to the architect for approval. Once approved, then the panels can go into manufacturing. And it's the same way for all the panels on the exterior walls. Okay, the next video is going to detail how we do multi-story construction. This system is also quite easily adapted to multi-story construction, and I'm going to run through an example very quickly on that. Starting with the footer, first step is, as we saw before, installing the wall panels, and the other steps I'm not going to show you: rebar, embeds, putting on the shuttering, pouring the walls, and then taking the shuttering off. So the result is a concrete wall on the lower floor. The next step would be to either pour a concrete floor or steel with metal deck floor or a precast concrete floor. And then, as you can see, the process starts all over again. And that's how multi-construction can be done. The perfect concrete wall system, from shop drawings through manufacturing through field installation. I'm going to spend more time in detail describing the system. I mentioned before that there's rebar locators that allow for precise reinforcement location. In addition to that, I see in the future that composite reinforcing steel could be utilized in this system quite easily and installed in the factory due to its lightweight and shipped to the job site already installed. Continuous insulation, I can't stress this enough, that continuous insulation partition in the center of the wall serves three purposes. It's an air barrier, it's a vapor barrier, as well as a thermal barrier. Now, the material I talked about earlier was expanded polystyrene, which has an R value of about 5. There are other materials. Phenolic rigid board has an R value of 8. So The beauty of the manufacturing technology system is materials can be analyzed and determined in the future as to which way they're going to go, if they're going to go with different materials. So the manufacturing, unlike construction, does have R&D to improve the product. I mentioned the sustainable shuttering. Well, I propose to use plywood, and most building projects have a roof, and the roofs need roof sheathing, which is usually plywood. So I would propose that the roof sheathing gets delivered to the project early so it can be used as shuttering for the walls of the building. And once the walls are topped out, the shuttering that can be reused is reused for the roof. That's a great sustainable system and a lower cost for the project. I mentioned no expensive forming system to truck and maintain. The reason there's so few concrete forming contractors is because it's a huge investment for them, and every job they have to replenish their supplies and clean the forms, truck them from job site to job site, and maintain them in between projects. And not to mention they have to have a truck crane. Having the insulation partition in the center of the wall result in the perfect concrete wall system. I'm going to go through a few of the reasons why in this slide here. With a wall system where the insulation is on the inside, whether it's above grade or below grade, when the outside temperatures are colder than the inside temperatures, if there's any leaks or cracks at all in this internal wall, the warm vapor transmits through and hits this cold surface of the concrete and condenses and causes other problems: leakage, mold, decay, rot, bad odors. So on the next system, where the insulation is on the external face of the wall, whether it's above grade or below grade, the layer of insulation needs to be protected during the construction process and also during the life of the building. So there needs to be a protection membrane put out here to protect it. Now, in most southern states, this practice is frowned upon due to termites. Termites love to get into insulation and call it a home and get a way to get up to the roof of the building and eat up the roof system. So that is a downside for that system. Now, putting the insulation on both the inside and outside is even worse because all the problems with having it on the external side and internal side are still present. Okay, I mentioned that the water control layer of a wall is the highest priority for performance. And having a solid concrete partition exterior of the wall means that any finish can be installed without penetrating any of the control layers. The next highest priority is the air control layer. And it is continuous and it is verifiable. It is this continuous insulation partition in the center of the wall that is connected with the H-shaped friction fit connectors at all the joints. And I say it's verifiable because before any of the whole system of all the walls are installed, before any shuttering is in place, and it can be verified by a third-party inspector to verify that that is continuous. The third highest priority is the vapor control layer. There again, it's that insulation partition which allows drying to the inside and drying to the outside from the center of the wall. Differential vapor pressure from a typical building from the inside to the outside is usually a factor of 2 times. The entire cross-section of the perfect concrete wall system wall is a vapor control system with the benefit of concrete on both sides of the vapor barrier web. The concrete retards the flow of vapor by 3.2 perms per square foot per inch of concrete. No condensation on the interior face of the wall due to high vapor control performance. Therefore, no mold, no odor, no decay, and corrosion, resulting in a comfortable indoor environment. The thermal control layer, the fourth and last priority. Insulation is not exposed for long periods of time during construction, so there's no physical damage or sunlight exposure. Insulation is not exposed after construction to physical damage because it's protected with 2 layers of concrete. For systems where you have below-grade walls, since the insulation is protected, there's no need to poison the insulation to prevent the so-called insect interstate. Since the exterior is smooth concrete below grade, walls have many more options for waterproofing materials that are simple to install. I mentioned before that this negates the problem of thermal bridging. Here is a good example of that, where the typical wall with the insulation on the outside allows for thermal bridging and heat loss through this area. A typical 4 inches of expanded polystyrene at an R value of 5 will produce a R20, but with the thermal mass of the concrete on the inside and the outside greatly increases it with an effective R value of R42. Basically, the thermal mass slows down the heat transfer through the wall. It's very durable for the long term because the insulation, air barrier, and vapor control barriers are sealed in concrete and protected. Quality. Since these panels are manufactured, the web insulation, the shear connectors, the composite horizontal rebar are precisely placed and eliminate any field errors. Panel connectors ensure air tightness, these yellow H-shaped friction fit connectors. Since all panels as well as all vertical reinforcing are placed before the shuttering goes up, the entire system can be visually and third-party inspection all at once. Accurately placed reinforcement steel prevents cracking, and continuous impervious web results in durable protection against air leaks and water leaks. After shuttering is removed, visual inspection of the interior and exterior surfaces of the wall is performed to ensure a quality wall. Off-gassing of toxic spray foams, glues, sealants is eliminated because there are none. Now, the jury is still out on expanded polystyrene, how much off-gassing it has, but because in this system it's totally encased in concrete, there is no chance of that off-gassing to the inside of the wall, as there would be if this insulation was placed on the inside. Engineering, submittal, and manufacturing is minimal since the product has a small number of standardized components. These struts, these web members, these connectors. Shipping costs are minor since panels are lightweight with composite horizontal rebar and no heavy concrete to ship around. No equipment required to unload and install. Field labor is minimal since very few parts to install and only 2 types of panels, the straight wall panel and the corner panel, all with control marks along the top showing the field crews where they go. No expensive forming system to store, ship, erect with heavy equipment and maintain. Plywood shuttering can be used for other parts of the building. Plywood shuttering can be installed by any carpenter. Similar to installing drywall, it's very easy. It gets installed with a self-tapping screw, number 8 screw with a button head top. The composite struts and ties are designed for a 4 foot per hour pour rate, as well as full shear resistance when the wall is subjected to lateral loads. External wall system can be easily attached to the exterior concrete withe with no additional support steel. Since there is no exposed insulation on exterior, interior, no additional fire-rated materials need to be installed. Since the inner withe can dry to the inside, that's the inner withe of concrete is the inside face, can dry to the inside. No additional vapor barriers are required with the expensive flashing and tapes and sealants and adhesives. Below grade spaces, if this system is used for below grade, can actually be used as comfortable living and workspaces, reducing the need to increase the building footprint above grade. With the high cost of residential houses today, if you can use the basement as livable space, then that's a big benefit. The first cost of mechanical systems providing heating, cooling, humidity, air quality control are minimized, since this system solves all the problems of air leakage, vapor control, and thermal control in the exterior wall. Building envelope commissioning, which I think is going to be prevalent in the future in the United States, where the performance can now be predicted due to the ease of visual inspection all at once, right before they put the shuttering on. Minimal mechanical systems result in lower energy use. Since panels are manufactured to a project, there is little or no waste. Reuse of shuttering on the project reduces trucking, equipment for erection, metal forms, and material use, which boils down to less fuel being consumed. Therefore, a smaller carbon footprint. So this is very sustainable. The concrete is durable. In some buildings, it's 2,000 years old. I know concrete is out for review right now as to whether or not it reduces the carbon footprint. Well, if you compare this to precast, the precast panels have to be trucked a long distance, which consumes a lot of fuel. Most concrete plants are very close to the job sites, so you reduce that trucking. Concrete itself, the cement consumes a lot of energy in the production of cement. However, there are technologies today that are being developed using crushed and ground up fly ash to capture some of the carbon to make the concrete closer to being carbon neutral. So keep that in mind, that concrete is becoming a better material to use for sustainable buildings. It's a long-lasting envelope with low operating costs, and it has a much lower life cycle cost, according to the GBES. Demand-controlled ventilation can be used with additional HVAC savings, since the buildings are more airtight and vapor controlled. This system is engineered. I have engineered it, and I have all the calculations as backup if the right company wants to develop it with me. Okay, now let's talk about price. The easiest access to information that I found in the 4 market segments was single-family homes. So I'm going to run through this example based on just the single-family homes, not the healthcare, university, or hotels. According to the National Association of Home Builders, there were 2 million new homes built in 2019. 600,000 of those included basements. And let's say we start out marketing the system for basements, and we capture 1% of those homes in the first year. That results in 6,000 projects, with a typical basement being 30 by 50, 9 foot tall. That yields 1,500 square feet of panels per project and 9 million square feet total panels. So using the 9 million square feet of panels, that would result in a market share of close to 85 million, only 1% of the market share. That is pretty incredible. So I think anyone who wants to manufacture has to market up or get ready for a huge influx of demand. I also did a cost comparison for a standard 8-inch wall with exterior insulation. So the 8-inch standard wall with exterior insulation versus the perfect concrete wall system. With the panel price of $10 per square foot, which I believe can be manufactured for much less than that, it shows that the panel system, or the perfect concrete wall system, is less expensive in today's dollars than the cast in place straight concrete wall with exterior insulation on it. So, whenever you have a project that improves quality of a building envelope, reduces field labor time at less cost, that is an industry disruptor. So to give you a little background on another industry disruptor, back in 1952, Carol Sanford founded the pre-engineered wood truss system, which today is on practically every wood building. What he did was basically he reduced the field labor time. He improved the quality because now it's an engineered system, and he did it at less cost. That's why everybody has that system now. So, in 2021, Perfect Concrete Wall System developed a new concrete wall system, greatly increasing the use of concrete over other systems, and has marked the beginning of the concrete industry resurgence as the preferred building envelope system that is changing residential, commercial, and institution building all over the world. That's what my vision is. So, point of this presentation, as I started out, I'm looking for the right company to develop the perfect concrete building envelope, strong in the concrete industry, has state-of-the-art in composite plastics manufacturing partners, is an expert in precast-like shop drawing production CAD/CAM systems, a company with a brand, with presence in trade shows like World of Concrete, Precast, ACI, BSC, USGBC, Fine Home Building Yearly Summit. Engineering capable, not afraid or financially limited to meet the huge market and make concrete the building envelope leader. So, in closing, I'd like to state, I'm an engineer. I'm not an entrepreneur. I serve mankind by making dreams come true. Here's a cover of my patent that I'm proud of, and there is the number. Thank you for listening.